Hello, my name is Nick Vendegiesen. I'm Professor of Water Resources Management. In the previous two lectures, we saw that the world needs water for food and for cities. Now we will look at the tools at hand to supply water. First we look at reservoirs, and the next time we will look at groundwater. In an ideal world, our water supply would exactly match our water demand. Never would there be too much water, never would there be too little. In reality, water supply is extremely variable. To ensure a steady supply of water, we have built reservoirs as buffers against natural variation. Let's say that we need a steady supply of drinking water for a large city, but that the discharge of the river supplying the water varies strongly over time. By building a reservoir, we can filter out these variations and ensure a steady supply. A reservoir needs to be able to bridge periods of low supply. A simple way to design the minimum storage capacity of a reservoir is the so-called ripple diagram, which you see here. The wiggly line shows the cumulative inflow over time into the reservoir. The straight line is the minimum constant yield from the reservoir that we would like to see. By drawing lines parallel to the yield line that are tangent to the cumulative inflow, we can readily determine the storage capacity needed to bridge periods with low flow. Of course, also our demands vary largely over time, but the same principle holds, except now we should use the ratio of supply over demand as input and would like to ensure the output is as close to 1 as possible. Actually, reservoir operations is a mathematically rather advanced field because small improvement in operational improvements quickly translate into large financial gains. There are continuous efforts to improve predictions of supply and demand. We use reservoirs for many purposes. Perhaps the most important function is hydropower generation, whereby water from the reservoir drives turbines that generate electricity. The largest dams in the world are all hydropower dams, such as the Shasta Dam shown here, which was built during World War II in California. Irrigation is the second most important purpose for which we build reservoirs, ensuring that water is available throughout the year, also during dry seasons. Because sunshine and temperature tend to be better during the dry season than during the wet season, agriculture productivity is very high. This is the Pantabangang Dam that irrigates more than 100,000 hectares in central Luzon in the Philippines. Reservoirs do not only supply water in times of water shortage, they can also regulate water during floods by storing excess water. In this case, one wants the reservoir to be empty most of the time so it can buffer floods. River navigation also demands certain water levels. To maintain water levels upstream or downstream, dams are constructed in rivers for the main purpose of navigation, such as here in Koblenz at the mouth of the Mosel River. Even though our need for drinking water is small compared to our need for water to irrigate crops, we do want to have drinking water of good quality year-round. That is why large cities often do have drinking water reservoirs, such as the Schoharie Reservoir, which is one of 19 reservoirs that supply New York City with drinking water. New York City obtains some of its drinking water from a distance of over 250 kilometers. There are very few dams that fulfill only one purpose. Once you have a dam to store water for irrigation, you might as well let the water flow through turbines to generate electricity. This Chandel Dam in India does exactly that, as well as supplying nearby communities with household water. The management of multi-purpose dams is especially tricky when the reservoir has to serve contradicting demands, such as flood control and hydropower. For flood control, one wants the reservoir to be as empty as possible, while for hydropower, you want to have it as full as possible. Over the past 100 years, humanity has built many reservoirs. A staggering 10,000 cubic kilometers of water has been stored in man-made reservoirs since 1930. This is equivalent to a sea level rise of 3 centimeters. Let's look at the reservoirs of the world in the 20th century with this Gapminder software. You see different circles, each circle is a country. The bigger the circle, the bigger the country. The colors refer to different parts of the world. On the y-axis, you see the amount of storage in millions of cubic meters, and on the x-axis, you see the population. We start in 1900, and let's see what happens over the course of the century.
Not much is happening, especially in terms of reservoirs, but then we see something moving. Countries are moving. And this is where we are at the end of the century. And we basically see that most countries huddle in this corner, but that there are 6 different countries when it comes to storage and population. One is, for example, India, a lot of people, not so much storage, however. Another one is Brazil, that is really coming up in terms of storage. But another one that's interesting is Canada. A lot of storage, not so many people. But the three main countries that are important for the 20th century, of course, are the USSR, the United States, and China. And let's look a little bit more at what they did in the last century. We go back to, let's say, the early 1930s. We see that in the 30s, as part of the New Deal, the United States starts building reservoirs, continue during the Second World War, and then actually in the 1970s starts to sort of level off. If we go back in a little bit more detail and look, for example, when exactly everything starts, we see that during the Second World War, the United States built a lot of reservoirs still, and that only after the Second World War, the USSR starts to catch up, and they continue to build dams at an extremely high rate until about 1990, when the wall collapses and the USSR falls apart. You see that in the United States already earlier, maybe early 70s, they start to stop building the reservoirs there, maybe out of environmental considerations, maybe because all the good places were taken. But in any case, after 1970, there's not much going on anymore. When we look at China, we see an interesting pattern as well. We see sort of two jumps. The first one is the big jump forward, which in many ways was a big jump backward because 10 million people lost their lives. And at the same time, there was a lot of forced industrialization, which caused this huge jump in the reservoirs built during that time. Then we see a sort of a normal development in China until, again, the 90s, when China starts really developing, and we see an acceleration again in the number of reservoirs being built. So you see, in a way, the whole history of the 20th century reflected in reservoir construction around the world. Now, it's interesting for history, but can we also do something for water management? Well, let's see what happens, for example, if you put area on the x-axis. And you see that, well, maybe these countries sort of fall on a bit on a line. Maybe there is sort of like a linear correlation between how big a country is and how much storage they have, which would not be unsurprising. And there's one country that clearly falls under this line, and that's Australia, which also makes sense because although Australia is a large country, most of it is desert, and you would not build reservoirs there. In order to see better if there is indeed a good correlation between the size of a country and the amount of storage, we can also directly plot storage per area for these different countries just to see if they would fall in one line. And well, maybe, but you see that there's actually two outliers here, Uganda and Ghana, who are not so big as a country, but they have huge reservoirs. So these outliers sort of skew the scale, if you want. If we make this a log scale, that we see that, and you do see that indeed, more or less, when you're a country that is diverse, you can expect to have about 10 centimeters of storage. Now, that makes it, of course, also very interesting to see where are there no reservoirs yet. And then we go to countries like Algeria or Libya, well, or Saudi Arabia. Well, these are all desert countries, so that makes it a little bit difficult to see. But if we change the color maybe to the rainfall, so we get some idea about if it's a very dry country or not, we get to see some countries that are not dry and they still do not have a lot of reservoirs. For example, the Congo. The Congo can supply all of Africa twice with the electricity needed just by its hydropower potential, but also a country like Papua New Guinea, for example, obvious with the mountains and a lot of water, has almost no reservoirs yet and will have them soon. Myanmar, only 3 millimeters. I'm pretty sure they will go very high because it's also a very water-rich country, and the same holds for a country like Colombia. They will all move up to 10 centimeters or well above that.
If we assume that for non-desert countries there will be, on average, 10 centimeters of storage, we can say that by now 60% of all reservoirs that will ever be built have been built. In other words, of all the reservoirs that will be built eventually, about 40% has not yet been built. Over the decades, sentiments about especially large dams has fluctuated. First, they were seen as the great heralds of progress in the Depression years. But clearly the construction of large dams brings many negative consequences, such as displacement of people, loss of habitat, and disturbed downstream flows. In the United States, many dams have been or are subject to decommissioning, such as here the Glines Dam, in order to restore natural flows. At the end of the 20th century, The World Bank hardly financed any dams due to the negative impacts. In 1997, the World Bank initiated the founding of the World Commission on Dams. This commission has produced a set of guidelines that balance negative and positive aspects of large dams. Reservoirs will be with us for quite some time to come, and that we will build a good number in decades to come is also sure.